Welcome back. We are doing Thermodynamics 1 homework. This is homework number 5, which is energy balances, first law analysis on open systems. Okay. And so the second problem is out of Koretsky's textbook 2.59. So I go to 2.59. Let's see here. Okay. Air enters a well-insulated turbine. Air enters this turbine, here it comes out. I have a rotating shaft here. Okay. Let's see here. Air enters a well-insulated turbine, so well-insulated, that means it's going to be adiabatic. Okay, we're going to put these little hash marks on there. Okay. With negligible velocity, okay, so V squiggly in is approximately 0. Okay. 4 MPa, P in is equal to 4 MPa. T in is approximately 300 degrees Celsius. Okay. The air expands to an exit pressure of 100 kPa. P exit. The exit velocity and temperature, so V squiggly exit is about 90 meters per second, and the temperature exit is at 100 degrees Celsius. Okay. So it drops about 200 degrees Celsius. The diameter of the exit, so diameter of the exit is equal to 0.6 meters. Okay. Determine the power developed by the turbine in kilowatts. You may assume air behaves like an ideal gas through the process. Well, that's not a bad assumption. Okay. Alright, well, we got a picture. We got a boundary. We got some assumptions. We're going to assume that there's no boundary work. There is shaft work. We assume it's adiabatic. We are going to assume that delta PE is approximately 0, but not delta KE. It gives us a velocity, so it probably wants us to account for kinetic energy changes. Now it still might be negligible, but we're gonna account for it because it gives us that information. Okay. We're gonna assume it's steady state. And we're going to assume no leaks. Okay. So we do our mole balance. N dot I minus exits. N dot E equals dN dt of my control volume. That goes to 0 because it's steady state. I don't have any leaks, so I only have one thing coming in. I only have one thing coming out. They are equal to each other because they're equal to 0. So N dot I equals N dot E, which is going to equal my N dot. Okay. Let's see here. Okay, why do I need to know the diameter? Well, now I'm assuming a circular pipe. Okay, it says diameter, so that's a pretty good assumption. Okay, well, if I know the circular pipe, that means I know the cross-sectional area, I know the velocity, I can back calculate the volume, the volumetric flow rate, which means I can back calculate the molar flow rate using PV equals nRT, because I'm also assuming an ideal gas. Okay, so I'm assuming an ideal gas. Okay. Now, there might be some other assumptions in there. I would want to assume heat capacity is constant, but it didn't say heat capacity is constant, so I'm not going to get to assume heat capacity is constant. So, but I want to. And I think in this case, for this analysis, I'm going to. Last analysis, I didn't. Of course, last analysis, I also didn't assume it was an ideal gas, and I should have. Okay. So we're going to assume the heat capacity is constant just to keep the mass simple. Cp is approximately constant. Okay. Now, is that a good assumption? No. I dropped 200 degrees Okay, so that's a really poor assumption. I'm just doing it to simplify the math in this case. So at home, you're doing this for homework. Should you assume it's constant? Well, all right, fine. I won't assume it's constant. I'm just trying to make my life easy because it's late. All right, so summation of n dot I hi plus 1/2 v squiggly squared I plus gzi minus summation of n dot he plus 1/2 v squiggly squared e plus gze plus q dot plus work dot equals du plus ek plus ep. Those go to 0. dt. Control volume, that all goes to 0 because it's steady state. I have no heat transfer, I have work, I have stuff coming in, I have stuff coming out. I don't have much of a velocity coming in, I don't have a change in potential energy, I do have a velocity coming out. But again, really the velocity is there to figure out what my flow rate is more than anything, but I'm going to account for it anyways. Okay, and so when I'm all said and done, I have n dot I hi minus n dot he plus 1/2 v squiggly squared e plus work dot equals 0. Okay. All right, and these ends are constant. I mean, not constant. Well, they are constant, but they're also. What I'm saying is that they're the same. Okay. And I'm trying to find the work. So I've got work coming out of this, and I'm trying to figure out what that is. And so work is going to equal n dot he minus hi minus 1/2 v squiggly squared e, plus, minus a minus. Yeah, okay, this is an ideal gas, and so work dot equals n dot cp dt from t in to t exit plus 1/2 v squiggly squared e. All right, and I'm gonna have to worry about I've got a v squiggly squared. That's in the kilojoules per kilogram unit, so I'm going to have to kind of I'm going to have to make sure I watch out for my unit conversions. Again, it's going to be pretty negligible compared to everything else, but I still have to account for it. Okay, and then of course the CPDT becomes, so my n dot again is going to be P exit. I do have a T exit, so P exit, V exit, which is going to be the pi over 4 diameter exit squared. That's my volume, or that's my area, times my velocity. So V exit. V squiggly square, V exit. Okay, so there's my over R T exit. There's my molar flow rate. Okay, times that guy, which is going to be from T in T exit of A plus BT plus D over T squared dt. Plus 1/2 v squiggly squared e. Okay, I integrate that. So no is in I know them. So I know that, 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 I know that. Okay, so I know everything except for work. I can solve this, but just to do my integral quick, it's ATE minus T in all times R plus B over 2 TE squared minus T in squared minus D 1 over T exit minus 1 over T inlet. Okay. Plug, chug, and rinse and repeat. Again, this little bit is going to be negligible compared to everything else. And you'll see that when you do this problem, like, okay, I mean, change 200 degrees. So even if we assumed approximately 7/2 R, so 7/2 R is about, we'll say 30-ish, 30-ish, and that's, so 30-ish times 200. So it's going to be 6 kilojoules. 6 kilojoules. Whereas the other one is going to be more like, 4,100 kilojoules per kilogram. I don't exactly have a kilogram here. I don't know what I do have, but I probably do not have a kilogram here. So again, the molecular weight is about, 29-ish, okay? And so I'm not going to have much of a velocity change. The energy change associated with the kinetic energy change is going to be negligible compared to what I have with respect to the enthalpy change. So.